So we finished chapter 2, in which we have gone through the postulates of quantum physics. And as I told you, this was going to be very dense. Many concepts have been introduced. Now it's time to start practicing them on some specific quantum systems. At this point, the more old textbooks would introduce the material point, which is the object that has position and momentum as degrees of freedom. This requires an infinite dimensional Hilbert space. The more modern textbooks, also inspired by quantum information science, they rather go into what is called a two-level system or a qubit, and that's what we are going to do here. So the chapter 3 will be devoted now to a specific quantum system, which is the two-level system, also known as qubit, from quantum bit, bit being the unit of information. And this is the system that we have seen already in 6 quantum pieces, right? So we will have a vector space of complex dimension 2, and this is what defines the two-level system. Now we are going to do it in a more thorough way than what was done in chapter 1. I will not follow exactly the same line as in the lecture notes, but at the end the material will be the same. So at least you have 2 complementary point of views on how to introduce these matters. Not too different either, right? Okay, so let me start with introducing a basis that in 6 quantum pieces we called H and V for horizontal and vertically polarized. Here, for a reason that will become clear a bit later, I will call this computational basis plus Z and minus Z. And the plus Z will be usually represented by 1, 0, and the minus Z by 0, 1. Okay, so this is our computational basis. Now, the first object I have to introduce that you have not seen before is a series of matrices. So we are going to move quite quickly to the operators and come back to the states later. So the matrices I want to introduce are the so-called Pauli matrices. And so the Pauli matrices, there are 3 of them plus the identity, depending how people count them. So the traditional Pauli matrices are written like that. Sigma 1, also known as sigma x, is this matrix. Sigma 2, also known as sigma y, is this one. And sigma 3, also known as sigma z, is this. What are the properties of these matrices? Let's go calmly through them and see what happens. So these are the properties. First of all the 3 Pauli matrices and all of that we are going to define later are both Hermitian and unitaries, as it's easily checked. They are Hermitian because they are equal to their conjugate, and they are unitaries. This you can check rather easily by checking that they actually the multiplied by their transpose gives the identity. So the sigma k are both Hermitian. Let's say this is evident. Just look at them. And unitary. Okay, let's check the unitarity. Unitarity means that, remember, that means that sigma k dagger times sigma k should be equal to the identity. That's the definition of unitarity. And now sigma k dagger is equal to sigma k. It's Hermitian. So this is sigma k squared. And you can rather easily check with a few lines of calculation, 1 line of calculation, that sigma k squared is actually indeed equal to the identity for all of them. Second property. the three Pauli matrices plus the identity, so the identity, sometimes written sigma 0 for obvious reasons, sigma 1, sigma 2, and sigma 3 form a basis of 2 by 2 complex matrices. So in other words, every complex matrix that I've written here, every linear operator, A can be written as sum over k 0 to 3, ak sigma k, with ak usually complex. And now, if I want a Hermitian operator, so now every Hermitian A can be written also like that, but with ak real. Okay, another important property is the commutation relations between Pauli matrices. These are, actually this is what defines, you will see later also with angular momenta, this is a very important definition of the Pauli matrices. So the commutation relations are quite, are cyclical. So you can check that you have something like this, sigma 1, sigma 2 commutator is equal to essentially sigma 3. And the essence is there is a 2i in front, the 2i sigma 3. And as you probably can imagine, and you can verify, this is true if I do sigma 2, sigma 3 will be equal to sigma 2i sigma 1, and sigma 3, sigma 1 will be equal to 2i sigma 2. So we can write it in general as sigma j sigma k is equal to 2i epsilon j k l sigma l, with these being the tensor you might have already met somewhere in your life, that is such that ejkl is equal to plus 1 if jkl is an even permutation of 1, 2, 3, is minus 1 if jkl is an odd permutation of 1, 2, 3, and is 0 in all the other cases. So if, for instance, if j is equal to k, E1, 1, 0, E1, 1, 2 would be 0. Okay? So these are the commutation relations between the Pauli matrices. Now, the last point that I want to make is that here I said that every Hermitian operator can be written like that. I should have, now that we have the products, we can check that every unitary operator, now let me write it in red, so I have all these pens here that I'm getting. Every unitary operator can be written like this. Now the condition is that, can be written like you don't need the identity. It can be written as sum over k equal 1 to 3 uk sigma k with sum over k equal 1 to 3 uk squared is equal to the identity. To 1, sorry, that's the condition. Okay. What you have here defines the Pauli matrices and some of the main properties. Now, let me erase the properties and continue playing with these matrices and with those vectors and look at the eigenvalues and eigenvectors of these matrices. Okay, so it is clear that our two computational basis vectors are the eigenvectors of sigma z. It's not by chance that these are called plus z and minus z. indeed, we see from here that so sigma z applied on the vector plus z, well, it gives plus 1 times the vector plus z, and sigma z applies to the vector minus z, it gives minus 1 on the vector minus z. So the eigenvalues of this matrix are clear, 1, minus 1, and they are associated to these vectors. Now, as it turns out, these other matrices have the same eigenvalues and different eigenvectors. So if we look at these, it's a not too difficult exercise to prove that the eigenvectors of this one are plus x written as that, sorry, written that in that basis it looks like this. So it means represented 1, 1 over root 2, and minus x is the same thing with a minus sign here, so it would be 1 minus 1 over root 2. Again, eigenvalues plus 1 for sigma x, eigenvalue minus 1. And this one, sigma y plus y is equal to 1 over root 2. Similar to this, but with an I sign here for eigenvalue plus 1 of this matrix, minus y, same with a minus. So again, here, this would be 1i over root 2. This would be 1 minus I over root 2. Okay, so these are the eigenvalues and eigenvectors of these matrices. Now that we have these tools, we are going to describe more in general the states and then some important operators that are used in the two-level system. So as you see, for the moment, I have not really spoken about states and operators. I've just given you these three matrices, these three operators that we need to know, and some of their properties. Okay, now let's use all this knowledge to start discussing states and other operators. Now, first of all, what is the most general state in C2? Well, a state in C2, if you give me a basis, it's any linear combination with complex coefficient of that basis. For instance, so therefore, any psi can be written, if I choose to use the computational basis. Again, remember, every state is a good state, every basis is a good basis. If I choose the computational basis to write psi, I could write it as something like C plus Z plus C minus Z, which represented as a vector would be simply C plus C minus with C sigma in complex for both sigma equal plus and minus. And of course, because we normalize our vectors, we assume that C plus square plus C minus square is equal to 1. These, for the moment, there's nothing special. But now, I'm going to write this object in a more appealing way, and you will see what I mean by more appealing, hopefully. So, what I'm going to write these coefficients with other parameters that at start may seem a little bit surprising. Why do I write it like this? But it will turn out to have a very interesting physical meaning. So let me write this guy like that. Okay, now, relax. Let's see if we have done something wrong here or something special. Well, first of all, one thing you may be suspicious of is what happened here. This was a complex number. Now I've got a real number. What happened here? Well, here I exploited the famous, remember, equivalence up to a global phase. Okay? So if I had a complex number here, I could just take it out as a global phase and remove it by saying this state is equivalent to the other one. So for the it's okay to take this one as real. This one, of course, must remain complex. This is a relative phase. It describes the difference in phases between the two. Alternatively, in some textbooks, you find the same thing written like that. It's also fine. It distributed this relative phase between half here and half there. Again, it's always the same because remember that when we deal with vectors, we have this equivalent up to a global phase, which would mean that if I take this one as a factor, I would get this. Right? Okay, so this is what we have been doing here. Now, the notation is, okay, here the normalization is taken care of because cos squared plus sin squared is equal to 1, so that one is fine. Now you may ask, why have you written theta over 2? But you could have written cos theta. Okay, now we are going to see these. And in order to see what it is, let's compute the projector on this state. The projector psi, what is it? Well, it's cos theta over 2, ei phi sin theta over 2, matrix multiplication with cos theta over 2, e minus I phi, remember the bra you have to take the complex conjugation, sin theta over 2. And we open it up, this gives cos square theta over 2, here sin square theta over 2, let's see, up there, e minus I phi cos theta over 2 sin theta over 2, and here e I phi cos theta over 2 sin theta over 2. And you may say, well, this does not look particularly appealing either. But this one is very appealing because you can check, and this I will leave it as an exercise if you want, that this object is equal to this. This is exercise. Is equal to 1/2 the identity plus, let's see if I remember by heart, it should be like that, sin theta cos phi times the Pauli matrix sigma x plus sin theta sin phi times the Pauli matrix sigma y plus cos theta sigma z. Now you see that my theta over 2 that were coming out from here have become thetas. And that's where I wanted to get. Now look at this expression and see if you recognize something. Look at these. These are the component of a unit vector represented in spherical coordinates, right? You have a unit vector n equal to nx, ny, and z in Cartesian coordinate. If you write these components in spherical coordinates, I mean, connect the Cartesian component with a spherical coordinate component, you would get exactly these: sin theta cos phi, sin theta sin phi, and cos theta. And this is a vector of length 1, right? So what have we found? And now, first I will tell you what we have found, then I will write it in a more compact way that sometimes people get a bit scared of, but we have found that a pure state is labeled by a unit vector in R3. Let me say it again. Every psi in C2 can be labeled by a unit vector in R3, in other words, a vector on the unit sphere S2. Okay? This is a mathematical result. Now, we have two things to do now. One is to write this thing in a more compact way, just for your sake. Then we have to discuss what is the meaning of this vector. Does it have a physical meaning? Okay? So let's first rewrite things in a more compact way. That might be a bit scandalous the first time you see it. Yeah. So you see, I have found this projector. And now, so first of all, let me change the notation. Therefore, this state, written like that, I will call it plus n, okay? Because it's associated to the direction n, indicated by the angles theta and phi on the unit sphere. And we have found this is the projector on that state. Now, let me define vectors in a more let's say, rigorous way. So my vector n would be nx unit vector in direction x plus ny unit vector in direction y plus nz unit vector in direction z. And now I'm going to do something that you will find very abstract, but you will have to get accustomed to it at some point. I'm going to define a vector of operators. So bear with me. The vector sigma will be equal to sigma x ex plus sigma y ey plus sigma z ez. Now, what is this object? Okay, this is a kind of messy object. From the point of view of the R3 space, it's a vector, right? This is a vector in R3. From the point of view of the Hilbert space, it's an operator, or at least the components of the vectors are operators. Now you may say, well, this is how do I represent this thing? Well, like this. All right? What does that mean? Okay, I will give you the physical meaning of this guy later, but think for a moment that later we are going to describe position. Right? Position is also a vector, but it's going to be an operator. So the position, I write it Q, I think, or maybe X. The position operator will have to be a vector in space, because the position itself is a vector in space, right? So position operator will be something of the same type. Where these guys are operators, and we will see in chapter 4 what they do, and these ones are the vectors in R3, right? So this represents a physical quantity, again, examples are coming, that in real space is a vector. However, because we're doing a quantum theory of it, the physical quantity is not represented by a series of numbers, but by operators. Again, I don't pretend you have a great feeling with that, but it will come. Okay? So this is one of these things that I cannot expect you to understand the first time I say it, but it will come at some point, I can tell you. All your seniors have got it. So now if I have this notation, I can write this beautiful projector plus n plus n. I can write it in a very compact way as 1/2, 1 plus what? Well, this looks like the scalar product. Forget for a moment, these are matrices. This is like the scalar product between nx sigma x, ny sigma y, nz sigma z, the scalar product in R3. So I can write it like this. Sorry, sigma. Where this is the scalar product in R3. So this is Ej is equal to delta Ij for these guys. With these, it's almost obvious what is the state that is orthogonal to plus n. Well, it's minus n, right? It's the state that points in the opposite direction. And minus n would be equal to, well, you just replace plus by minus. And the fact that they are orthogonal, you immediately see, because if I take the sum of the two, plus n plus minus n minus n, this is the projector on the whole space. Yeah? It's the identity, this term cancels, and this projects on the whole space. And you have a tutorial in which you are asked to write, given n, what is minus n in spherical coordinates. There's a function of theta and a function of phi. You plug them in here, and you find that the vector is indeed the orthogonal. This, I think, is a tutorial that you are asked to do at some point. Okay, so now let me wrap up this part before giving some kind of physical interpretation. What have we got? We have got a generic state. And remember, every state is a good state, so this is as good state as anybody else. We have got its orthogonal. Okay, I've not written it down how it looks like. It would look like that. Maybe let me write it down as a vector how it would look like. The orthogonal to that one, the minus n, looks like sin theta over 2 plus z minus ei phi cos theta over 2 minus z. Okay, this is the orthogonal. So we have a basis, a generic basis that represents what? Well, something pointing in the n direction and something pointing in the opposite direction. And we have the two projectors that describe these in terms of the Pauli matrices. Essentially here we have everything we need for the description of every state. Now, let me comment a little bit more about this vector n. Erase something. This vector. This vector n is called it's called block vector, and it has a very nice property that you can check again, is that n is the expectation value on the state n of this vector sigma. So in other words, this would be plus n sigma x plus n sigma y plus n sigma z plus n. Good. Now we know everything about the block vector. The block vector is expectation value of this operator. The components of the block vector are expectation values of the state, so of the Pauli matrices over the state. Well, good. Now, what is the physical interpretation of that object? Now, if you think carefully, the answer is we don't know, right? We are dealing with a generic two-level system. How can I tell you what is the physical interpretation? This will depend on which two-level system we are considering. So now I'll give you some examples, and I will tell you if, for these examples, we have a simple interpretation of the block vector or not. In the case not, well, then the block vector is just a label of the state. What is a label? Well, look, when I bought this shirt, you can say the label is the color, right? I can go to a catalog and find the red shirt, the blue shirt, the yellow shirt, and so on. Now, red, blue, yellow, and so on are not the shirt. It's a label of the shirt. When I buy it, I expect to get a shirt, not a color. Okay, similarly here, the state is the state in the Hilbert space. If you want to order a state online, if you want Alice to send Bob a state, there are these kind of problems, what you say, well, you can specify the block vector. I would like a qubit in the state indexed by its block vector. It's like the color of the shirt. And Alice will send to Bob a qubit that is not n, is psi, but the state psi, the coefficients of psi, are those indexed by n. Okay, now physical examples. And let's see what we can do. So, examples of qubits. Okay, the most famous, not exhaustive. The most famous of all is what is called the spin half, that you've already met in chemistry. This is really the thing that the electron has. I can only take two values. Okay, so the spin half is actually a magnetic moment. Its full expression, magnetic moment, is an object that has units. And in fact, the spin would have some unit h bar over 2 on top of the Pauli matrices. Now, the Pauli matrices are dimensionless. These are just algebraic objects. This number here in front gives the units of a magnetic moment. Actually, yeah. Maybe here I might have said something imprecise. Let me check sorry, for the magnetic moment, I always forget that one. There is another factor here that is called the gyromagnetic factor. That indeed gives to that object, I will tell you later what the thing without the gamma is, that gives this the unit of a magnetic moment. Anyway, there is a number here, and then there are the Pauli matrices. Now, for this one, the block vector is very nice. Because the block vector, you see, if I say, I make many measurements of this object, on average, in which direction is the spin pointing? So the average direction of the spin, you can consider it as the classical direction of the spin, would be gamma h bar over 2 times the block vector. In the state, of course, plus n. So for the magnetic moment, for the spin half, the block vector has a clear physical interpretation, is the direction in which the spin is pointing. And remember, I told you already, spins do not point only up and down. They can point in any possible direction. Is a qubit, so if you measure in one direction, you can get either plus in that direction or minus in that direction, but any direction is a good direction. Okay, so this would be, in this case, the block vector of the state n is just the average, the direction of the average direction of the spin. Okay, so this spin has an interpretation as also as an angular momentum. This we'll see in chapter 5. Chapter 5. Okay, this is the one that I wrote before without the h bar, the gamma. This is the definition of an angular momentum. Okay, another example now. We are going to do, let me see what I have in the lecture notes. I have yes, I have to tell you something for your information before continuing. So, when it comes to spins, people like to change a little bit the notation. It can happen. So what we called plus z is sometimes written up, and what we call minus z is sometimes written down, and what we call plus x is occasionally denoted by an arrow like that, and they call minus x is occasionally denoted by an arrow like this. Again, remember, what goes into the cat doesn't matter. Okay, so this is just a notation that I tell you. For this guy, there will be a very strange notation of this type that you will learn in chapter 5. So plus z here is usually written 1/2 plus 1/2, and minus z is usually written 1/2 minus 1/2. And you will learn the meaning of these numbers when we go into chapter 5. For the moment, no need to rush. Now, the other famous example of spin half is, of a qubit is a polarization of a photon, or more precisely of an optical mode. This is the one of 6 quantum pieces. So you remember that here, what we call plus z is usually written horizontal. What we call minus z is usually written vertical. This one has nice interpretation for all the direction as well. What you call plus x is usually plus 45 degrees, or diagonal polarization, linear, minus x, linear, minus 45. Then what are plus y and minus y? The plus y would be circular right, and minus y would be circular left. Okay, now you can ask, what is the block vector for for polarization? Oh, that one is not so easy. Notice one thing, that horizontal and vertical, we normally write it like these, okay? Horizontal and vertical, these are how it is. However, in Hilbert space, horizontal becomes this, and vertical becomes that. So there is like an angle, here there's an angle 90 degrees, here there's an angle 180 degrees. So the block vector is not, doesn't have an immediate physical interpretation. However, just for your information, the people in classical optics, already in the 19th century, before quantum physics, they found out that it's convenient to parameterize polarization with what we nowadays call Pauli matrices. They call them the Stokes parameters. So just for your information, the block vector here would be called the Stokes vector. And you can check online what are the Stokes parameter. It's really for classical light, classical polarization. Just a beam of light, polarized, you want to characterize the polarization, you use the Stokes vector. It is equivalent to the block vector for spins, or for qubits in general. Okay, another example of qubits, 2 energy levels. Now, as you know, an atom, for instance, an electron in an atom or something, has many energy levels. Now, you may be, so then that's the correct description of that atom. But in some experiments, and it's very frequent, you may be in a situation where actually you are only addressing 2 of these levels. Imagine an atom that has an energy structure like this, for instance. I don't know, I'm just inventing something. And there is this gap that is unique, right? All the other gaps are bigger. Then by addressing the atom with that frequency that corresponds to this gap, well, you can move the electron or whatever from here to here and back, and you never go to the other levels, right? So if you do an experiment like this, and again in quantum optics we do many of those, or at least a thought experiment, then your atom, even if it has many levels, you can consider it as a 2-level system. Here the notation would be, well, typically plus Z is called the ground state. It doesn't need to be the ground state absolutely, it's the ground state of your qubit, and the minus Z is called the excited state. Now, for this case, we don't have a nice notation for things like E plus G, and we don't have an intuitive interpretation, and we don't have an intuitive interpretation for the block vector. It's really like the block vector is really a parameter that describes the states. Very good. Now, to finish this lesson, I just want to mention something about measurements on spins, on qubits. Measurements. Well, Well, first of all, physical examples. You know that usually if you have a beam of particles that is polarized in spin, you have the Stern-Gerlach magnet. This is for a beam of neutral particles with spin. Really spin in the sense of magnetic moment. So this is this magnet that is a gradient, usually is represented something like this. So it is a gradient of magnetic field in this direction, and then the particles go in and are split up or down according to their spin. So I come in with any state here, and the spin up goes up, spin down goes down. And then there's a screen, and you see these. I'm sure you've seen these in some previous module. For polarization, we have seen the polarization measurement we have seen in 6 quantum pieces can be done with a polarizing beam splitter that splits horizontal goes in this direction, vertical goes in that direction. I enter with an intermediate thing. It is exactly the same structure. It's just that this is a photon, this is an atom with spin, neutral atom with spin. For energy levels, I will not tell you how to measure them. So there are various strategies of measurement. Again, the specific strategy depends on the physical system, as you clearly understand now. Now let me just tell you the algebra of the measurement, right? So let's go with the algebra of the measurement. Yeah. Algebra of a projective measurement. We do only projective measurements. So imagine I have the state plus n, and I enter into an object that is supposed to discriminate in the direction m. Remember, projective measurement is related to a basis. A basis in this case could be only two vectors that are orthogonal, which means that there is another direction m in which I'm going to find either plus m or minus m. And again, this direction can be any, this direction can be any. You don't always measure spin to be only up or down in the z direction, can be any direction. What are the probabilities? Exercise. The probability for plus m given plus n is 1 plus vector, scalar product of the two block vectors over 2. The probability of minus m given plus n is 1 minus, all these are hats, over 2. Again, sum equal to 1, and everything is fine. So these are the statistics of any measurement. Now you could remember what we did with the observables, right? We said that we could define an observable that is, for instance, plus 1 times the projector on plus m plus minus 1 times the projector on minus m. Okay, this would be one of these observables. We call them A. Okay, what is this object? Well, this object is a kind of Pauli matrix. Let us open it up. This is plus 1 times, remember what the projector of this one is, 1 plus m times sigma over 2 plus minus 1 times 1 minus m times sigma over 2. Go through this. This is just m times sigma, sometimes written sigma m for convenience. So it's very frequent for people to say, I measure sigma m. You don't really measure sigma m. You measure in the basis plus m and minus m, and this is the observable that gives the eigenvalue plus 1 to plus m and minus 1 to minus m. Okay? So this is the... now a very generic observable, last observation for this class. Any observable that must be Hermitian right? So any observable will be a combination of the Pauli matrices and the identity. Let's try it. So if I have an observable A, well, is it certainly, there are two eigenvalues, lambda plus and let's say A plus and A minus, let's say, and two eigenvectors. We don't know what the eigenvectors are, plus m, and then there's another eigenvector, minus m, minus m. We agree that this is the most general possible observable, right? I can choose my basis, and I can choose my eigenvalues. Okay, and now you can rearrange these things again with the same trick. This projector is this projector is that, and you would get something of this type, A plus A minus over 2 times the identity, plus A plus minus A minus over 2 times this sigma m. So in other words, any observable on one qubit, on a two-level system, can be written as such. In the next lecture, we are going to look at the dynamics. So in particular, we will consider an observable of this type that is the Hamiltonian. Now, this may sound surprising for you now, but think about it. The Hamiltonian for a spin is not p squared over 2m plus v of x, because there's no p and there's no x, right? So the Hamiltonian can only be one of the operators. Again, it may or may not have an easy physical meaning, and it will be an operator of this form. This will be for the next lecture. We finish here.